South Korea has reached a new milestone in the field of fusion energy.
Also called an artificial sun, has set a world record by maintaining a temperature of over 100 million degrees Celsius.
KSTAR just blasted to a record-breaking 100 million degrees Celsius, way hotter than the sun's core at 15 million degrees. This Korean project, called the Artificial Sun, is smashing through the limits of nuclear fusion, where atomic nuclei combine to unleash massive energy. But what if we're on the brink of something even bigger?
Scientists are working to harness a clean and unlimited source of power, just like stars in the sky do.
Join us to expose what this could mean for the future of our humanity. The future of energy, KSTAR's revolutionized potential. The Korea Superconducting Tokamak Advanced Research, or KSTAR, has made a big step forward in building a working nuclear fusion reactor. Since the early 1900s, scientists have been fascinated by nuclear fusion. This process merges two atomic nuclei into a larger one, releasing energy. It could provide more energy than it uses, like how the sun produces energy. Tokamak devices like KSTAR aim to copy the sun's fusion reactions here on Earth. These achievements are not just steps towards sustainable energy. They put KSTAR at the leading edge of nuclear fusion research. This could lead to a future where our global energy needs are met in a new and powerful way. But this isn't the end. There's more progress to be made. There are about 250 Tokamak machines around the world. The word Tokamak comes from a Russian phrase that means toroidal chamber with magnetic coils. In the late 1960s, two Russian scientists figured out how to contain plasma at very high temperatures using this technology. Yong Soo-na, a professor at the Department of Nuclear Engineering at SNU, pointed out that the success of the STAR experiment brings us closer to creating the technology needed for nuclear fusion energy. Since last August, the STAR has done 110 plasma experiments. The results will be shared at the IAEA Fusion Energy Conference next May. The ultimate goal is to make the machine run continuously for 300 seconds at temperatures over 100 million degrees Celsius by 2025. Suk Young-yoon, the president of KFE, is excited about the institute's new phase as an independent research entity in Korea. They are dedicated to leading research to achieve the long-term goal of harnessing nuclear fusion energy. But there's still a long way to go before this becomes a reality. Imagine a world where energy is so abundant and clean that it no longer limits our growth. Around the globe, governments, researchers, and companies are racing to achieve a breakthrough in fusion power, which could eliminate our need for fossil fuels. This could revolutionize technology just as profoundly as the discovery of fire did thousands of years ago. Some people doubt it's possible, but one company, Helion Energy, believes they are close to mastering this technology. The company's leader, David Kirtley, dreams of building machines that will give us cheap, clean, and abundant energy within our lifetimes. Helion Energy aims to create fusion generators capable of producing 50 megawatts of safe, clean electricity, bringing fusion power closer to reality for our homes. So, why is fusion power so highly sought after? Ideally, the perfect energy source would be endlessly available, environmentally friendly, compact, and very safe. Fusion power, which generates energy by combining atoms under extreme conditions, fits this ideal perfectly. Although scientists have been experimenting with fusion since the 1950s and have managed to achieve atomic fusion in labs, no practical way to generate electricity has yet been demonstrated on a large scale. Let's explore how fusion power can change our energy future. The promise of endless power. The potential of fusion power is huge. Just 1 gram of Helion's fusion fuel, deuterium, could power a home for an entire year. This fuel is almost inexhaustible and found in all of Earth's water. The main fuels for fusion are isotopes of hydrogen, protium, deuterium, and tritium. Recently, better fusion reactions have been found using deuterium and a rare isotope of helium, helium-3. When fused, these elements produce helium-4 and release a vast amount of energy. But let's understand nuclear fusion a bit more. Atoms are the smallest units of matter that form all elements, consisting of a nucleus surrounded by electrons. The nucleus contains protons and neutrons. At extremely high temperatures, atoms form a plasma, a hot mix of charged particles. In this state, atoms lose their electrons, and their nuclei, being positively charged, usually repel each other unless they collide with enough energy to overcome this repulsion. When these collisions happen with enough force, the nuclei can fuse due to a powerful force called the strong nuclear force. This fusion creates a heavier nucleus and releases energy. Nuclear fusion releases energy millions of times greater than burning an equivalent mass of fossil fuels. In nature, fusion happens in the sun, where gravity creates immense pressure and heat, allowing hydrogen atoms to fuse into helium, which powers and warms our planet. Earth receives energy from the sun, which plants use in photosynthesis and humans harness through wind, water, and solar panels. But replicating fusion on Earth is extremely challenging. Without the sun's gravitational advantage, a man-made fusion reactor must operate at even higher temperatures and efficiencies. It must confine and control a plasma so hot it could vaporize any material, while efficiently converting this tremendous energy into usable power. The delicate balance of maintaining the right conditions for fusion, where the fuel is dense enough and particles are sufficiently close, is crucial for the success of fusion energy. But achieving this is no easy task and will require incredible innovation and perseverance. Achieving nuclear fusion, where atomic nuclei combine to release energy, is one of the most challenging projects ever. It involves heating elements to very high temperatures to make them react. These conditions need to be maintained long enough for many reactions to occur. This complex task requires engineering and physics working together to manage high temperature, stress, and pressure, while also making the process cost-effective. Helion, a leading company in fusion technology, uses purple glowing rings moving at over 1,000,000 miles per hour to achieve fusion. There are several methods to achieve fusion, mainly divided into 3 categories. Magnetic fusion keeps hot plasma within a magnetic field to start a continuous reaction. Inertial confinement fusion compresses plasma to high densities using powerful lasers in very short bursts. A third method, magneto-inertial fusion, combines elements of both by compressing and heating the plasma with magnets. While these methods have successfully initiated fusion reactions, scaling them up to produce electricity on a large scale is still a big challenge. The main problem is not just producing energy, but creating more energy than is used in the process. Helion focuses on directly converting this energy into electricity, skipping the traditional method of using heat to produce steam that drives turbines. Next, we'll see how Helion is making fusion energy a reality. Helion's quest for fusion energy. Since 1951, nuclear power plants have worked by splitting heavy nuclear elements like uranium-235 to release energy. This old process still uses heat to make mechanical energy and generate electricity, a method from the 1800s. Helion, however, is exploring new ways to harness energy directly from fusion without steam turbines. This idea was imagined in the early days of fusion research, but was limited by the technology available at that time. The process starts with the formation stage, where small amounts of fusion fuels, deuterium and helium-3, are introduced into a chamber and superheated into plasma. This is done using oscillating magnetic fields, like how a microwave works. This step is crucial as it sets the stage for the complex reactions that follow, aiming to harness the vast potential of fusion energy to provide a sustainable and powerful source of electricity. But remember, this is just the beginning. The journey to make fusion a practical source of energy is full of hurdles, but the rewards could be immense, offering a cleaner and virtually limitless power source for the future. Behind me is the tube where we inject gas for fusion processes. These processes work at very high temperatures and magnetic fields. The tubes are made from a special glass called fused silica quartz, which can handle these extreme conditions. When we turn fusion fuels into plasma, we pump energy into the system. We use electromagnets powered by huge currents, millions of amperes, to compress and heat the fuel. These large currents are created using something called capacitor banks. These electromagnets are key for magneto-inertial fusion. They pulse with large currents, heating up through a process called ohmic heating. This heating creates a pressure force of up to 100 megapascals or more, which strains the magnetic coils. These coils must endure intense heat, the pulsating nature of their operation, and high electrical voltages. The capacitors store electrical energy for a few seconds and then release it almost instantly, powering the electromagnets wrapped around our device. This rapid action changes the plasma's magnetic field into a toroidal shape, known as a field-reversed configuration. Understanding the electromagnetic properties of plasma is crucial for these fusion devices. Using a Tesla coil, helium gas is heated until its electrons are stripped from their atoms, forming plasma, a hot mix of ions and free electrons. This plasma can conduct electricity and interact with magnetic fields. When electromagnets are activated, they generate an electrical current that loops within the plasma, creating a magnetic field around it. Unlike other methods, our field-reversed configuration plasma confines itself with its own magnetic field. This self-organizing property lets us compress, heat, manipulate, and transport the fusion fuel efficiently. Once the field-reversed configuration form at both ends of our device, magnets fire in sequence, pushing them towards each other at speeds over 1 million miles per hour. This process, like squeezing a tube of toothpaste, ramps up the magnetic field behind the fusion fuel, driving the plasma forward. These accelerated field-reversed configurations then enter the main fusion chamber, where they merge into a larger field-reversed configuration, colliding and converting their motion into intense heat. This primes the fuel for fusion reactions. In the heart of the machine, we rapidly boost the magnetic field, compressing the plasma with incredible force, over 10 Tesla, to intensify the fusion process. Now, let's dive into Helion's unique approach to fusion, the blazing heart of fusion technology. A unique feature of the field-reversed configuration approach is its high beta, meaning it operates under high pressure. Every time you compress the plasma using a magnetic field, it's like squeezing a balloon. The internal pressure and temperature rise, triggering fusion reactions. During operation, the Polaris fusion core becomes momentarily the hottest spot in the solar system. The materials facing the plasma inside a fusion device must withstand higher thermal loads than those experienced by spacecraft re-entering Earth's atmosphere. The first wall of the fusion generator is especially critical, shielding the core that reaches temperatures over 100 million degrees. Though no material can survive direct contact at such temperatures, the fusion plasma doesn't actually touch the wall thanks to a vacuum boundary that insulates it. Still, the intense electromagnetic radiation and high-energy neutrons from the fusion process constantly bombard the wall, challenging even the toughest materials. Finding the right material for the first wall is vital for advancing fusion technology. At 100 million degrees Celsius, deuterium and helium-3 atoms collide with enough force to fuse into helium-4. This reaction is uniquely suitable for direct energy conversion, unlike typical fusion reactions that emit most energy as neutrons. Deuterium. Helium-3 fusion releases energy through an alpha particle and a high-energy proton, making the energy easier to harness directly into electricity. Inside the heart of Helion's fusion reactor, fusion reactions take place where plasma turns matter into new energy, boosting the reactor's magnetic field. As this field strengthens, it interacts with the reactor's magnetic systems, changing the magnetic flux inside. This flux change then creates an electric current in the machine's coils. This current is cleverly captured and redirected to power the reactor's capacitors that energize the surrounding magnetic systems. The main goal of this process is to efficiently compress and heat the fusion fuel until it ignites, then quickly cool it down to harvest the generated electricity, introduce fresh fuel, and start the cycle again. Helion's generator, designed for this rapid cycle, has a system for venting the high-temperature gases produced after each reaction cycle, like an exhaust system in cars. This part, called the diverter, separates and processes the fusion byproducts. some fully reacted and some not, while also capturing leftover energy to convert into electricity. The design also includes advanced engineering to handle the high temperatures and remove any air from the system, ensuring the best environment for fusion. Helion delivers these bursts of fusion-generated electricity to the power grid through quick, millisecond-long pulses. This pulse system allows for fine control over the reactor's output, similar to adjusting an engine's RPM to match the energy demand. But this isn't the only challenge. Helion's main goal is the fast commercialization of fusion energy, aiming to connect their electricity to the grid at competitive costs. Despite the technical difficulties, the fuel needs are surprisingly low, with a small amount of deuterium fueling millions of pulses. While deuterium is abundant, the reactor also uses helium-3, a rare isotope proposed to be mined from the moon because of its buildup in lunar dust from solar winds. To tackle the scarcity of helium-3, Helion has developed a patented process to make it from the more common deuterium. This process also creates helium-4, boosting Helion's ability to keep their fusion reactions going. The company sees the challenges of fusion not just as scientific puzzles, but as engineering problems that can be solved through ongoing design and testing. Finally, we'll look at the big goals and impact of fusion energy. The future of energy, fusion's promising horizon. Measuring the system is key to making it better. Helion uses various detectors and tools, like neutron detectors and alpha particle detectors, to directly measure the fusion reactions and their outputs. These measurements help improve the system's performance, guiding the development towards reliable commercial energy production. Helion's method of producing fusion energy is similar to strategies used in other high-tech industries, focusing on scalability, cost reduction, and market adaptability. They envision a network of small, cost-effective fusion reactors, like gigafactories, which could transform energy production. The ultimate goal is to make fusion power an affordable and essential part of the global energy mix, with predictions of very low electricity costs once operational. Helion's dedication to bringing fusion power to the market highlights its potential to play a crucial role in meeting the world's growing need for clean, sustainable electricity. Helion continues to push the boundaries of what's possible, determined to make fusion energy a reality for everyone. At Helion, we believe fusion power doesn't replace renewable energy, it complements it. Today, most of our energy comes from burning fossil fuels, which greatly adds to greenhouse gas emissions. Fusion power offers a zero-carbon alternative, especially useful in places where renewable energy like solar or wind isn't common yet, such as in many developing countries. Areas that already use a lot of renewable energy, fusion can provide power consistently, even when the sun isn't shining or the wind isn't blowing. This makes it perfect for heavy-duty industrial energy needs, potentially replacing fossil fuels and existing nuclear reactors. Unlike traditional nuclear power, fusion has a much lower risk of major accidents. Fusion energy needs very specific conditions to keep a reaction going, making accidental meltdowns, like those in fission reactors, unlikely. Fusion reactors only use small amounts of fuel at any time, which can be stopped quickly to prevent any runaway reactions. Also, fusion creates much less radioactive waste compared to fission. The waste it does produce is less harmful and loses its radioactivity within about a century, making disposal and storage easier. But that's not the most exciting part. Fusion's potential as a safe, affordable, and zero-carbon energy source opens up many possibilities for the future. For example, if fusion power becomes widespread, it could make desalinating water much cheaper, helping to solve global water scarcity issues. It could also support the switch to electric vehicles, with many cars possibly being battery-powered by 2035. Small modular fusion reactors could provide flexible power solutions for remote or specialized locations, like large factories. The path to commercial fusion power is often compared to the development of computers, with rapid technological advances. Just as the computing industry has grown quickly, key performance metrics for fusion are improving at a similar pace. It's becoming more likely that we could achieve significant milestones in fusion, like generating net electricity, within this decade, with companies like Helion leading the way. However, making fusion a competitive and cost-effective technology will be a long process. But the idea of using the same power source as the stars to provide limitless clean energy is an inspiring goal, worth the extensive research and development efforts. This journey involves a mix of science, technology, engineering, and math. For those interested in understanding these innovative technologies, there are educational platforms that simplify complex scientific principles into manageable and interactive lessons. Could fusion power really be the ultimate solution? Or are we overhyping its potential? Leave a comment and subscribe for more.